Okay, thank you very much. Good afternoon, everybody. My name is Mike Kirby. So I'll just tell you a bit about our satellite, which is one of the satellites that will be flying on the QB50 mission. Right, I'll start with providing you an overview of the satellite and the basics of the satellite. And then I'll discuss some of the specifics that I feel makes the satellite quite special. And in the end, I'll speak a bit about the ACS of the satellite. Okay, so as I said, I'm from the ESL in Stellenbosch in South Africa. This satellite, the Aerosat, is the third satellite that's developed at the ESL. The first two was larger satellites, Sat and Sunsat. It's also the second CubeSat from South Africa. The first one was developed by CPUT, also in Cape Town. The funding for the satellite was half from leftover funds from the SAT project and half from internal funds. At the moment, we have two full-time engineers working on the project. I'm one of them. Two part-time engineers / postgrads, of which one is a doctorate and one is a master's. 8 full-time postgrad students doing research on various technological aspects. And then we've got more than 4 other staff members, including lecturers and technical staff such as solderers, etc. Okay, so there you can see a picture of the satellite and all the components of the satellite, of the main bus. It's a 2D satellite. We're using the ISIS QB50 skeleton. We found that to work very well for integration and also for separating the science unit from the rest of the bus. The orbital average power we generate is more than 2 watt, and the usage is less than 1.9 watt for the full operational mode. We use VHF uplink, UHF downlink. We've got an S-band high-speed downlink for streaming data down, and satellite will be 3-axis stabilized. Okay, so the first interesting part I want to talk about is the antenna feathers. We had this idea of using the beryllium copper feathers at the back of the satellite as for a dual purpose. The first being the VHF, UHF antennas. The length of the antennas was chosen to be resonant for VHF and UHF frequencies, and you can see an antenna beam pattern. And the second use of the feathers is for passive aerodynamic stabilization. And this is specifically useful for the QB50 mission because of the low altitude orbit. So yeah, it works pretty much like the feathers in the back of a dart, stabilizing the system in the velocity, the satellite in the velocity direction. The mechanical design of the system is done by CPUT in partnership with us. We're using a trapdoor mechanism to release the satellites, to release the antennas, which is rolled up into these containers. The antenna elements itself is made from beryllium copper strips that is tempered into a curved shape, like a tape measure, to give it stiffness. Right, the next part is our solar panels. So at first we were not going to deploy solar panels, but after some calculations we realized that to provide sufficient power throughout the entire orbit, we would require to deploy the panels. And the reason for this is because of the orbital decay, we expect because of the atmospheric drag with the low orbit. So here's some pictures of the panels. The manufacturing of the mechanics was done by Bachmann Systems, which is a manufacturing company in South Africa. I think I have a little video of the panels popping up. No, I'm going to try. Videos always fail. Alright, so the reason for deploying, here you can see a graph. Basically for different beta S angles, so the angle which the sun makes with your orbital plane, for very large angles, you would have enough power for a normal undeployed state, because you will have no eclipse and the sun shining on the side of your satellite the entire time. But for very low beta S angles, you would not generate enough power. So we deployed the panels to 42 degrees, which we found the optimal angle to provide more than 2 watts orbital average power throughout the entire lifetime, even though we have orbital decay. Alright, the next part of the satellite is the gravity wave experiment, which is scientific experiment that Wagner Systems came to us with. It's a device capable of measuring gravitational effect, not in the way that not in a way that's measuring force, but actually measuring the gravitational density or wave or gravitational effect directly of this mass. So with measurements we've done so far, we've miniaturized the system for them so that we can fly it on the satellite. And with measurements so far, we can definitely measure the influence of large bodies such as the moon and the sun. We are possibly, I say possibly because I don't want to make claims yet, until we've got good data, but we measure deep space anomalies, single events, ripples we measure. We possibly demonstrate gravitational shielding by showing that when the sun, the moon goes behind the earth, we see a definite change in our measurements. And we can possibly use this to measure gravitational disturbances within the earth because of earthquakes, etc. So just a bit of data. I just want to focus on the local sunrise and sunset here. This is just a 2-day recording of data, and you can very clearly see a drop in offset with the local sunrise and a climb in the sunset again, and the drop in the sunrise and climb in sunset. The next part of the satellite is CubeSat version 2. CubeSat is one of the fine sun and radio sensor that's being flown on the ADCS bundles. This is the second version of this device, which just uses a higher resolution camera for higher accuracy, and has the capability of storing 2 images in memory while doing detection. So you can use it as a grayscale imager throughout the orbit and download these images in clips. CubeStar is our miniature star sensor with only a mass of only 56 grams, nominal power usage of only 320 milliwatts. Yeah, it's capable of outputting quaternion measurements once every second, and it has an accuracy of 0.01 degrees 1 sigma across bore and 0.03 in roll direction. Right, in terms of the ADCS, we are using the standard QB50 ADCS suite but we're using the higher resolution CubeSat. So we've got the 3-axis magnetic resistive magnetometer, the fine sun and radio sensors, core sun sensor, 6 core sun sensors, single-axis rate sensor, single-axis momentum wheel, and 3-axis magnetometers. So an important part of the ADCS would be the effect that the feathers will have on the satellite. And for that we needed a good model of the atmospheric density. And here Professor Amanstein did some modeling, some simulations, and here we just show the normalized densities for eclipse and for sun parts of the orbit. So the first controller we use is the detumbling controller, which just uses a B-dot magnetic control to damp the X and Z rates and to align the orbital, the body Y-axis with the orbital moment. And then we use a Y-Thomson control to get the controller to get the spin controller to get the satellite into a Y-Thomson spin. So here's a simulation of the detumbling controller. So the reference Y rate given is the -3 degrees per second. We use a SGP4 orbital model for perturbations and an IGRF 10th order magnetic model. Here the control loop is done at 1 second, 1 hertz. Initial rates is as shown there, and you can see in the simulation the satellite being controlled to the Y-Thomson -3 degrees per second spin. After that we go into Y-wheel mode, which is the 3-axis stabilized mode. So then the sun vectors and major vectors from CubeSat is also used, and the full state estimation is run. The Y momentum wheel controller is then activated, and Yes, and the momentum of the satellite is absorbed into the Y wheel. So for this simulation, for the first part, you can see, actually, if I go later. Yeah, you can see the first part, we're uncontrolled, and then the B dot and Y spin is done for half an orbit, and then you've got the, at the end of the second orbit, we ramp up the wheel, absorbing that spin into the wheel, and then going to full stabilized mode. So this is just the simulation of the satellite in the Y wheel mode for different altitudes, because for similar to with the solar panel case, we want the satellite to be stable for the entire orbit, the entire mission lifetime, from 350 down to, let's say, 200 kilometers. So yeah, in the simulation you can see in orbit A, we've got at 350 kilometers, and in orbit B roughly 250 kilometers. You can see in both cases we've got pointing accuracies of way below the QB50 specifications, and at less than 2 degrees Pichron yaw, and less than 4 in the orbit B. Yeah, thank you very much.
Thank you for your presentation. Do we have any questions about? Yes?
Just interested to see how you guys shape your brilliant cover. How do you guys work with it, and or how easy is it to work with?
The Beryllium copper is actually pretty easy to work with. You can buy the strips standard, and for shaping it we use a mold. We make a mold, sandwich the strip into between two parts to give it the curved shape, and then first we anneal the material and then temper it to keep it in that state. But it's pretty easy to work. It's relatively high temperatures required, so you need a good furnace. So for annealing, I think it's 800 degrees or something like that, and for tempering, I think in the order of 300 degrees or something. I'm not 100% sure, but it works very well, and it provides a very good memory. Yeah.
Any other questions? So I have also one question. So you have very, let's say, even airplane-like shape with wings and tail and everything. Have you analyzed how stable is this configuration and how it affects the decay time related to other QB50 satellites which are not with the deployable panels?
Yes, so in the nominal state, the satellite will be flying obviously with the panels deployed to the sides. So it's not really increasing the frontal drag area that much. So in terms of deorbiting and dragging the satellite back, I don't think that has that big of an influence. We certainly have to do more full orbital mission analysis of that deorbiting effect. And obviously the feathers at the back also increases the drag slightly. In terms of the stability of the satellite, it's all modeled in the atmospheric simulations we've done. And in that control simulations we've done includes the yaw effect that the feathers at the back would have, and also the effect that the Earth's cross-wind would have on the satellite. Because obviously you've got this co-rotating atmosphere of the Earth pulling the satellite to the side. And that's all included in the simulation.
Okay, thank you very much.